Okay, so today we're going to talk about the last planet that we have on our list to talk about, which is not a planet anymore. It used to be a planet, now it's not a planet, it's something else. We'll talk about why that is, and we'll talk about what we've learned about Pluto in just the past decade or so. We've gone from knowing almost nothing about, first of all, Pluto wasn't discovered until the 1930s. Pluto is very far away and very small and gives off very little light. You need a fairly powerful telescope to even see it. So we didn't know Pluto existed until the 1930s. It was given a name. It was considered the ninth planet. And but we didn't really know much about it because even in our most powerful telescopes, it just shows up as a tiny, tiny speck of light. In the, I think, 1980s or so, early 1980s, we discovered that Pluto has a moon. We give that moon a name. That moon's name is Charon. Sometimes you'll hear people say Charon or even pronounce it almost like Karen. I say Charon. And that moon, again, we didn't really know much about because it's so small and so dim and so far away. The Hubble Space Telescope was able to kind of map these aren't photographs exactly, these are surface brightness maps. Because Pluto does rotate and because its brightness changes slightly as it rotates, we could make some guesses that, yeah, Pluto and Charon both have light and dark surface features, but we really didn't have a photograph of Pluto or Charon until we actually sent a space probe all the way to the Pluto system. That spacecraft was called New Horizons. It flew by the Pluto system, I think, in 2015. I'll have to check the dates on that, or check your textbook reading. I'm not so good with all these space exploration dates. But we have, since the time of New Horizons, had clear close-up photographs of Pluto and Charon. Here's a photo taken of the Pluto-Charon system. By the way, this is to scale, and one of the things you will notice about Charon is it's really big relative to Pluto compared to any other planets and moons in the solar system. They are so similar in size that they were considered sort of almost a double planet. And you can see, even as we were kind of still far away from Pluto, we start to actually see surface features on both Pluto and on its moon. One interesting thing about the orbit of Pluto and Charon, because Charon is so big relative to Pluto, the center of mass of the Pluto-Charon system is actually outside of Pluto. I think we mentioned this before when we talked about orbits. The moon doesn't exactly orbit around the Earth. The moon and Earth orbit around their center of mass, but because the Earth is way heavier than the moon, that center of mass is inside the Earth. You can think of it as when two objects orbit one another, they orbit around the point where they would balance if you put them on a seesaw. So if you put the Earth and moon on a seesaw, that point where they balance would be inside the Earth. So as the moon goes around the Earth in a big orbit, the Earth just kind of wobbles around a tiny, tiny bit. But with Pluto and Charon, because Charon is so massive compared to Pluto, Pluto actually moves in a little circle outside of its orbit. They orbit around their center of mass. The other thing to recognize about Pluto and Charon is because of their mutual gravitational interaction with one another, they are tidally locked. Now, our moon is tidally locked to us, right? We always see one side of the moon because the Earth's gravitational forces and the tidal forces have slowed the moon's rotation so that basically the moon's day, how long it takes it to turn on its axis, is the same as a month. So its same face is always pointing towards us. Pluto has done that to Charon, but Charon has also done that to Pluto because Charon is so massive and Pluto is so small. They have both slowed each other's rotation so that one face of Pluto always faces Charon and one face of Charon only faces Pluto. So if you lived on Pluto and lived on the wrong side of it, you would never know that Charon exists. Charon is always directly above one point on Pluto's surface. Here's a nice close-up picture of Pluto. We see that it does have surface features. We see that it has some craters. You can see a few craters on Pluto's surface, but more notably, you can see a difference between these light areas and these dark areas, and you can see differences between kind of rugged, bumpy, textured terrain and relatively smooth terrain. One of the things I find most interesting about these things in the outer solar system is that we didn't really know what to expect before we sent these space probes there. I think I mentioned when we talked about Jupiter's moons, Io and Europa and Ganymede and Callisto. I think everybody kind of expected in the 1970s, before we flew the Voyager missions past Pluto, that they would be just gray rocks like our moon. They wouldn't have all these interesting features like, you know, the whole surface covered in ice with cracks in it, maybe an ocean underneath. This was all unexpected. Likewise, I think the fact that the surface of Pluto seems to be dynamic, it seems to be changing over time, and seems to have unexpectedly complex surface features, was a surprise to a lot of astronomers. Here's an even closer up picture of Pluto showing this bright region, which if you just think about, well, what does that look like based on just looking at pictures of the Earth, that looks like ice, right? It looks like Antarctica, and that's what it is, although probably not water ice. One of the things we see is mountain peaks peeking through this layer of ice, and so Pluto does have some kind of or at least in the past, had some kind of active processes that led to the creation of mountains. And the fact that these mountains kind of stick up above this ice is a clue that this ice wasn't always there, that this ice is kind of moving across the surface. In fact, when we look at these ice fields close up, they seem to have this appearance that we would associate with dunes on the Earth, that they're dynamically moving. Now, dunes on the Earth and sand are blown by wind. And you might say, well, wait a minute, does Pluto have an atmosphere? Is there wind on Pluto? Kind of, a little bit. We'll talk about that in a second. But these features certainly look dynamic. In fact, there's places where it appears that they've kind of flowed over the surface, gradually covering up what's underneath. The composition of Pluto as a whole is a mixture of ice and rock. The density of Pluto is between the density of a big ball of rock the size of Pluto and a big ball of ice the size of Pluto. So the density, the composition of Pluto is a mixture of what we would think of as rock and what we would think of as ice, but not just water ice, things like frozen carbon dioxide, frozen nitrogen. In fact, these glacier-like features on Pluto's surface are not H2O ice, what we would consider ice here on Earth, like in Antarctica. They are nitrogen ice, frozen nitrogen, the stuff that our atmosphere is mostly made of, right? You've probably heard of liquid nitrogen. If you take nitrogen and make it cold enough, you can turn it into a liquid. If you make it even colder than that, you can turn it into a solid. So these flows of ice over the rocky terrain are nitrogen ice that is actually moving across the surface and gradually covering up what we would more traditionally think of as the rocky surface of the object. So dynamic surface, interesting surface, complex surface, unexpected surface. We've learned a lot about Pluto in just the time since New Horizons flew by. Now, the space missions that we send to Jupiter and Saturn, like the Galileo probe that went to Jupiter, the Juno probe that went to Jupiter, the Cassini probe that went to Saturn, stayed in orbit around those planets for years and years and years and years. This New Horizons mission was just a flyby. It approached Pluto, it took a bunch of pictures, and then it kept on going out of the solar system. So we just have a few days worth of photographs from the New Horizons spacecraft. It didn't hang around and orbit around Pluto. It would have taken too much fuel to slow it down into orbit after we had sent it all the way from Earth to Pluto. Its mission is actually continuing. We'll talk about that in a second. So even from just a quick flyby, we have learned a lot about Pluto that we didn't know before 2015 or so. Pluto has something that's like an atmosphere. We used this word, I think, when we talked about Mercury. It's a very, very tenuous envelope of gases that we sometimes refer to as an exosphere. An exosphere is like an atmosphere, but just really, really, really thin. It consists of nitrogen, methane. Methane is really common in the outer solar system, right? It exists in the atmospheres of Jupiter and Saturn and Uranus and Neptune. Some carbon monoxide, and probably trace amounts of things like water vapor. But the atmospheric pressure is 1/100,000th of the Earth's atmospheric pressure, so almost no atmospheric pressure at all. But if there's gas and it's moving around on the surface, and it has billions of years to act, that pressure of that gas might be enough to move this ice around on the surface and cause it to flow into is something like a dune that we see in the sand on the Earth. So very, very slow, subtle, the word is not geological. Geological means Earth. Plutological processes are happening to shape the surface of Pluto's surface. Here's a close-up picture of Pluto's moon Charon. What do we notice about Charon? First of all, we notice that it's not perfectly round. And we, I think, talked about the fact that all planets and moons are round because they're experiencing equal gravitational force from all sides. If you take a big lump of anything and make it big enough, gravity will squish it into a ball, because a ball is the shape you get when the forces are equal in all directions. Right? That's why soap bubbles are perfectly spherical. There's air pressure pushing in and there's air pressure pushing out, and those forces are equal in all directions, and that makes it a sphere. The Earth is a sphere. It's almost a sphere. It's rotating, so it's a little bit elliptical. Jupiter, Saturn, the moon, and so on. Charon is just right on the edge of not quite being big enough for gravity to squish all the bumps down into a perfect sphere. So we can see at the pole, it's visibly jagged. The gravitational pull of Charon isn't strong enough to squish those bumps down into a perfect sphere. We also see a difference between this kind of highland and lowland area. Lowland with more craters, the highland with more of this kind of smooth, icy surface. And we also see this kind of reddish brown coloration that's really, really common in the outer solar system. We saw it in the cracks of Europa. We saw it in Neptune's moon Triton. This material is thought to be a kind of mixture of organic compounds. Carl Sagan, the astronomer, in the 1980s coined the name tholins just to describe the generic organic goop that we see on the surfaces of objects in the outer solar system, and we see that on Charon as well. I'm not going to say much about Charon. I will let the supplemental videos from YouTube kind of fill in the gaps on Charon and tell you a little bit more of what we've learned about it just in the past few years. Pluto has some other little tiny moons. If this bottom object is the size of Charon, these little moons, Styx and Nix and Kerberos and Hydra, are just a few tens of kilometers across, just little, almost like captured asteroids, like Mars's sad little moons, Phobos and Deimos. There are other things orbiting Pluto, but they're very, very small compared to Charon, which is almost as big as Pluto itself. So why isn't Pluto a planet anymore? A couple of reasons. One is that its composition is not like either the terrestrial planets or the gas giant planets. Terrestrial planets, Mercury, Venus, Earth, and Mars, are rocky. Pluto is not rocky. It's rocky and icy. It's much more like a comet or some other kind of object than it is like a planet. Second of all, its orbit is really wonky. Most of the planets in the solar system orbit in a ellipse that's pretty darn close to a circle and in a plane that's pretty darn close to flat. Pluto's orbit is very elliptical. It's very elongated relative to the other planets, and it's also very tilted. It orbits at a 15-degree angle to the rest of the solar system, very unlike the other planets. By the way, the orbit of Pluto is so elliptical that it's not always the furthest object from the sun. Sometimes it is closer to the sun than Neptune. In fact, I think right now it might be closer to the sun than Neptune. I have to look that up. I don't know exactly what year they cross back again. But Pluto's orbit is not like the other planets. Its composition is not like the terrestrial planets. Its size is really, really small. It's much more like a really, really big asteroid than it is like a really, really small planet. And it's not by itself out there. It's being orbited by an object that's almost as big as itself. And it turns out there are lots and lots of other Pluto-like objects out where Pluto is and beyond. So either, we're kind of faced with a decision. Either we have to call all of these other Pluto-like objects planets, or we just say that Pluto isn't a planet. And what we decided about a decade ago is, let's just call Pluto something else. And the planets stop at Neptune. Now, what is this something else? Well, there's a clue from looking at Neptune's moon, Triton. We talked about this moon, we talked about Neptune. Neptune's moon, Triton, is weird. And it's weird for a few different reasons. It is, like Pluto, a mixture of rocks and ices. About 55%, the surface is mostly frozen nitrogen, just like those nitrogen glaciers flowing across Pluto. Carbon dioxide ice, dry ice, and H2O ice. So it's mostly icy and not rocky. Mixture, once you get below the crust, it seems like it's a mixture of rock and ice. It's actually bigger than Pluto. It's similar in size, a little bit bigger than Pluto. Similar composition, similar density, seems to be made of the same sort of mixture of rock and ice. And one clue that Triton is weird is that it goes around Neptune the wrong way. What do I mean by the wrong way? Everything, almost everything in the solar system goes around the sun in the same direction. And the planets mostly spin in the same direction, and the moons orbit their planets in the same direction. That's because everything in the solar system formed from the same collapsing, rotating cloud of gas, like water going down the drain in your bathtub. It's all spinning around in the same direction. But Neptune goes around the wrong way. What could cause that? Does that mean that Neptune wasn't formed in the same way as the other planets? No, what it means is that it probably formed going around the sun by itself, and then at some point got captured by Neptune in this backwards orbit. It got stuck in Neptune's gravitational pull. In fact, if Pluto's orbit was a little bit flatter and not tilted at such a steep angle, it's possible that Pluto could have gotten captured by Neptune a few billion years ago. Because its orbit is tilted, it doesn't actually get very close to Neptune. That doesn't happen. But it seems like Triton is more like Pluto, and Pluto is more like Triton, than either are like independent moons or planets. There are other things out there beyond the edge of the solar system that are similar to Triton and Pluto and Charon. By the way, we see this reddish color, these tholins, these brown-red stains on the surface that we think are caused by ultraviolet light from the sun converting methane ices into organic compounds, carbon compounds, right? Methane is CH4. You bang with some radiation, you can get it to combine with water and nitrogen and other things and make more complicated organic compounds. We also see these things that look like volcano type things, these sort of ice geysers that we saw on Enceladus and maybe also Ganymede and Europa, that are like volcanoes, but instead of being molten rock shot out of the earth, they are molten nitrogen being shot out of the surface of these very, very cold moons. So we call them cryovolcanoes at one point. So we see these on all sorts of objects in the outer solar system. So these objects in the outer solar system share a similar story. What is that story? Well, this brings us to the question of where does the solar system end? Step away from the camera for a second and get a drink. The solar system does not abruptly end at some point in space. Here is the orbit of Neptune in yellow, the orbit of Pluto in blue, showing both that it sometimes comes closer to the sun than Neptune and that it's tilted at a much more extreme angle than any of the other planets. At the edge of the solar system, there is a region of space junk called the Kuiper Belt. The Kuiper Belt is filled with icy and rocky objects sort of left over from the formation of the solar system. Objects from the size of bits of sand and gravel to snowballs the size of your fist, to chunks of ice the size of cars and buildings, to objects as big as Pluto. Now, if you've watched a lot of science fiction movies, it's hard not to picture the asteroid field from Empire Strikes Back, right, where the Millennium Falcon has to dodge all these. It's not like that. There are thousands of space is big. So even though there's millions of objects out there in the Kuiper Belt, there's thousands of miles between them. So we can fly a spacecraft through the Kuiper Belt and won't get crashed into by rocks and boulders and chunks of ice. But there's a lot of junk out there, and there are a lot of big objects out there in the Kuiper Belt. The size of the Kuiper Belt, the inner edge is about the size of Pluto's orbit. That's 50 astronomical units, 50 times the size of the Earth's orbit. And it extends out to maybe 100 AU or 80 AU or so. The Kuiper Belt is a little tiny donut of orbiting debris inside of a much bigger sphere of orbiting debris called the Oort cloud. The objects in the Oort cloud are more like things the size of a grain of sand or a piece of dust or a snowflake, individual snowflakes. But all this stuff left over from the cloud that formed our solar system, little ice grains, little mineral grains, are still orbiting the mass of the solar system. It might take hundreds of thousands of years for a snowflake in the Oort cloud to go around an orbit around the sun once. So where's the edge of the solar system? Is it Neptune? Is it Pluto? Is it the edge of the Kuiper Belt? Is it the edge of the Oort cloud? It's not, it doesn't really have a hard stop like that. The Oort cloud is 50,000 AU in diameter. I've drawn it grossly out of scale. This would be so small you couldn't see it. It would be a little tiny dot. 50,000 astronomical units in diameter, the size of the Oort cloud. So the solar system doesn't just stop at Neptune, it keeps on going for thousands of AU out into space. You'll find little bits of junk orbiting the sun. If we look carefully in the Kuiper Belt, we find stuff. In 2003, we discovered the first Kuiper Belt object, the first large Kuiper Belt object. It was first given the designation 2003 UB313. It was originally named Xena because I think Xena Warrior Princess was still on TV in 2003. The official name from the International Astronautical Union for this object is Eris. We call Eris a trans-Neptunian object. That is just a generic word for any big thing we find further away from the sun than Neptune. And so now we consider Pluto to be the closest trans-Neptunian object, or Kuiper Belt, large Kuiper Belt object. It is actually bigger than Pluto. It is 1.5 times bigger than Pluto. So if Pluto was still a planet, then Eris would also have to be a planet because it's bigger than Pluto is. It is 97 AU from the sun. That's almost twice as far as Pluto is from the sun. So Pluto is not the last big object in the solar system. Eris is bigger, and it's way further from the sun. And we know that Eris actually has a little moon of its own. So if you want Pluto to still be a planet, guess what? Eris has also got to be a planet. And there are probably hundreds of other planets out there that we don't know about yet. In the years since we discovered Eris, we discovered Sedna, which is a little bit smaller. We discovered Quaoar, which is 800 miles in diameter, about the size of Pluto's moon Charon. So Eris, Sedna, Quaoar have just as much right to be whatever Pluto is as Pluto does. Here is Eris and Pluto and Sedna and Quaoar, along with Makemake and Haumea and Orcus, all Pluto-sized-ish objects beyond the orbit of Neptune. So we call all of these things either large Kuiper Belt objects or trans-Neptunian objects or dwarf planets, or sometimes just Plutoids, just meaning something out there that's kind of like Pluto. I don't love any of those names. Trans-Neptunian object is just a description of where it is, so that's what you'll see most often. Some of them have moons. Orcus has a little moon called Vanth. Quaoar has a little moon called Weywat. And there's all kinds of stuff out there. Some astronomers think that there might be an object as big as Mars out in the Kuiper Belt that we just haven't seen yet. Here's some more. Salacia, 2002 MS4, which I don't think has a real name yet. By the way, some of the scale info might be out of date. I think this image is from about 2010, 2012. Figuring out exactly what the sizes of these things is hard because they're super, super far away. The point is there's a bunch of junk out there beyond Pluto. And it's all kind of similar in size. Here's a size comparison. Here's the Earth, Mercury, Neptune's moon Triton, and Pluto are about the same size. Here's Texas. Here's the biggest asteroid, which is Ceres. And you see that a lot of these trans-Neptunian objects are similar in size to Ceres. By the way, the flip side of Pluto being demoted from smallest planet to biggest trans-Neptunian object is that Ceres was promoted from the biggest asteroid to the smallest dwarf planet. Ceres is no longer categorized as an asteroid because it is perfectly spherical and is massive enough to have pulled itself into a spherical shape. We now consider Ceres to be a dwarf planet. So what does this mean? This means that the solar system doesn't have a hard edge. It means that there's a whole bunch of stuff out there beyond the outer edge of the solar system that we still don't know very much about. We've never gotten close to a Kuiper Belt object other than Pluto, if you want to call Pluto a Kuiper Belt object. Now, what is the New Horizons spacecraft doing now that it has passed Pluto? It is going out into the Kuiper Belt and is going to rendezvous close. It's going to do a close flyby of some object in the Kuiper Belt. I'm not sure when that's supposed to happen. Maybe I'll make that part of the homework assignment for this week. When does New Horizons reach its first Kuiper Belt encounter? I wanted to say it's 2026, but it might be even further in the future than that. So there we are at the outer edge of the solar system. Here is a graph of the large objects other than planets in the solar system. The first thing to recognize about this graph is the scale is logarithmic. So it's in terms of astronomical units, 10, 20, 30, 40 astronomical units. So the orbit of Saturn, the orbit of Uranus. In that area, there's lots of asteroids. Beyond the orbit of Neptune, there is the orbit of Pluto. Here's Pluto. The circles represent the size of the object. But look how many other little things are orbiting right in Pluto's orbit. So this is the inner edge of the Kuiper Belt, basically, is where Pluto is. Pluto is sort of in charge of maintaining the inner edge of the Kuiper Belt. And then here's Makemake and Haumea and all these other objects a little bit further out from the sun. And then you get fewer and fewer as you go out further, although Eris is super big way out there at 70 AU, 2006, 2007. Maybe this scale is not logarithmic. It's not. It's just a linear scale in AU. So 70 AU is twice as far as kind of where Pluto is, around a little less than 40. Well, when Pluto's its closest, it's around 40. When it's furthest, it's around 50 AU from the sun. And who knows what's out there at 100 AU, 120 AU. There could be an object as big as the Earth out there. We wouldn't know about it because it's so far away. Why are we interested in this stuff out here? Why are we interested in the Kuiper Belt? Why are we interested in flying a spacecraft by a Kuiper Belt object? The reason is that all of the objects in the inner solar system have been changed over time by planetary processes that change their geological composition by squishing them together so they form different kinds of compounds, by chemical processes that are fueled by ultraviolet light from the sun. But the stuff out in the Kuiper Belt is essentially like a time capsule of the material out of which the solar system formed 4.5 billion years ago. So a small object in the Kuiper Belt is essentially a chunk of the material that the planets in the solar system originally formed out of. The reason we want to go out there and see what stuff is like, and maybe even someday grab a chunk of it and bring it back to Earth to study more closely in the lab, is because we would learn something by studying that material about the unchanged, unaffected, untransmogrified, just virgin material from the formation of the solar system. It's like going back in time 4 billion years and picking up a chunk of the material that the Earth formed out of. So that's why the Kuiper Belt is interesting to us. It's not just, oh, there's weird stuff that's kind of like Pluto, 60, 70, 80 light years away from the sun. It's that, sorry, astronomical units, not light years, 60, 70 astronomical units away from the sun. It's that those objects are literally pieces of the early solar system that have had very little chemical or pressure or light affecting them at all for the past 4 billion years. Okay? So I think that's all I want to say about Pluto and all of its little friends. I will leave the supplemental videos to give you some more details about some of the specific discoveries that New Horizon made, particularly about Charon. And next, I think we haven't talked about like asteroids and comets and stuff, more leftover junk, more little bits of the solar system. But we'll be done talking about the solar system, and then we're going to talk about sort of formation of solar systems in general, and what evidence we have for how planetary systems